All right, welcome. Today, we've got a bit of a royal math puzzle for you. We're going to find out if completely different paths can lead to the exact same hidden treasure. This whole idea is kind of the key to our entire journey today. It's like having a treasure map, right? You might see a few different routes sketched out on it, and they might look totally different. But a good map, a really good map, is always going to get you to that one spot where X marks the treasure. So, in the math world, those different paths have a name: equivalent expressions. Basically, they're just math phrases that look different on the page, but when you actually do the math, they give you the exact same answer. And that's our treasure, right? That single same value. Okay, so let's look at the two paths on our math for today. Path number 1 is super direct, just 12 divided by 3. But path number 2, it's a bit more winding. It's 4 times 3 and then divided by 3. So the big question is, do they lead to the same place? Well, let's find out.
All right, let's start digging. Our first clue is something you can practically touch and feel. We're going to get hands-on with this.
So I want you to picture this. You're the wise King Solomon. You've got 12 gold coins in your hand, and you need to split them up fairly between 3 different tribes. This makes it super concrete, you know? It's a real-world problem. The question is simple enough. How many coins does each tribe walk away with? Now, one really physical way to think about division is just repeated subtraction. I mean, if we're dividing 12 by 3, what we're really asking is, how many times can I take away a group of 3 coins before I have none left?
Okay, so let's do it. We start with 12. We hand out the first 3. Now we have 9. Let's do it again. We're down to 6. One more time. That leaves us with just 3. And that last subtraction, boom, we're at 0.
So how many times do we do that? 4. It took exactly 4 steps. So our first path, the 12 divided by 3, it leads straight to the number 4. Okay, now what about that other, more winding path? Let's check it. 4 times 3 is 12, and 12 divided by 3 is, well, it's 4. So there we have it. Our first hands-on test totally confirms it. Both paths lead to the same treasure. But hey, one clue is never enough, right? We need more proof. So let's look for our second piece of evidence. This time, it's a proof you can actually see. Sometimes the easiest way to solve something is to just draw a picture. So can we prove this visually? Could a quick sketch give us the same answer and back up what we just found? Let's give it a shot. First, imagine we're drawing out all 12 of those gold coins. Then we just start splitting them up into 3 equal groups, 1 for each tribe. We just hand them out one by one until we're left with 3 nice even piles. And if you just count them up, what do you see? Yep, each group has exactly 4 coins. The visual evidence is crystal clear. It confirms what we found before. Both paths definitely lead to 4. Okay, so we've got a physical proof and we've got a visual proof. That's pretty good, but for our final piece of evidence, we need the ultimate proof. Something that doesn't just work for 12 coins, but for any number, every single time. We need something like an unbreakable code, an abstract test. And this is where algebra comes into play. You can think of algebra as the universal language of math. It's what lets us prove things are true, always. It's pretty much the most powerful tool we've got in our treasure hunting kit. So let's set up our 2 paths using a little algebra. We'll just call our treasure x. So our first path is easy. X equals 12 divided by 3. Now that second path was 4 times 3 divided by 3, but we already figured out that just comes out to 4, right? So we can just write its simplest form, x equals 4. Okay, let's solve that first one. 12 divided by 3 is 4. So x equals 4. And the second one, well, it's already telling us that x equals 4. The results are, you guessed it, identical. And there it is. That's the final, definitive proof. The unbreakable code of algebra confirms it, beyond any shadow of a doubt. These 2 expressions might look different, but they are absolutely, perfectly equivalent. So after following 3 totally different clues, our quest is pretty much complete. Now it's time to step back, look at what we found, and reveal the real treasure we were searching for all along. Think about it. We took 3 completely separate routes. We started with that concrete physical path of repeated subtraction. Then we switched to a visual path, just by drawing it out. And finally, we brought out the big guns, the abstract and powerful path of algebra. And what happened? Every single path led us to the exact same place. And that is the real treasure here. It's not just the number 4. It's this amazing idea that in math, when things are truly equivalent, it doesn't matter which path you take. The truth, that single underlying truth, is always going to be the same.
And this whole idea that different paths can lead to the same truth, it really reflects a much deeper kind of wisdom, doesn't it? I mean, just like King Solomon used his wisdom to find fair solutions, we can use the clear logic of math to find a little more clarity and understanding in our own lives.
So that leaves us with one last question to chew on, and it goes way beyond math. Just think about it for a second. What other different paths in your life, maybe in your job or your relationships or even how you learn things? What if they're all just leading you to the very same truth?